Okay, good morning. I'd like to start off by reviewing the material from last time. So we're going to continue our discussion of form closure and force closure today. Okay, so let's begin by reviewing the main results from last time. Okay, so I motivated this material by asking what I think is a rather very practical question. Okay, so if I had some picture frame like this, and I wanted to make this stationary by using 4 pins. Suppose in one case I place the pins symmetrically in this fashion. And in another case, I place the pins asymmetrically, say in this fashion. Okay, so using 4 pins, so they have no friction, so there are 4 frictionless point contacts. Okay. All right, so I asked the question, which is better? Which is more stable? Which can resist external disturbances, forces, moments applied to this picture? Okay. Which is better? Okay, so of course you have to say what do you mean by better? Okay, so i.e. can resist external forces and moments. Okay. All right, so we set out on a 1-hour quest to answer this question in a precise way. Okay. So I won't go through everything, okay, but let's go over the main points in our argument. Okay. So these are frictionless point contacts. So that means forces can only be applied in the normal direction. Okay. So forces can only be applied in these directions. Okay. So let's call this F1, F2, F3, and F4. Okay. Furthermore, okay, these forces can only exert pushing forces. Okay, they can only push. They cannot pull. Okay, so we can write down explicitly the form of these forces. So let's pick a reference frame. There's our reference frame. Okay, and with respect to this reference frame, the forces can now be written in the following way. So F1 is going to be 0 minus x1. Okay. F2 points in the minus x direction, so it's minus x2, 0. F3 is 0, x3, points upward. F4 points in the plus x direction, so it's x4, 0. Okay, and it's important to remember, again, they can only push. So what that means is that these xi's, x1 up to x4, they have to be greater than or equal to 0. Okay, so only pushing allowed. All right. Okay, so if an external force is applied, so I'm holding this, so imagine these are 4 fingertips holding this object. If an external force is applied to the object, I need to generate forces with my fingers that can resist this external force. Okay? All right. So that leads to the next concept. We need the equations for static equilibrium. Okay? So static equilibrium. Okay? That means all the forces have to sum to 0. All the moments have to sum to 0. Okay? So sum of the forces equals 0, and sum of the moments equals 0. Okay? So then we have static equilibrium. The object is stationary. It doesn't move. Okay? Okay, so this is easy enough, right? Add all the forces, including the external force. Okay, make sure that sums to 0. Okay. Next, add all the moments, including the external moments. Make sure that sum is equal to 0. Okay. So if we write down all the equations, okay, I'm not going to do all the derivations here. Okay. What we get is an equation of the following form. Okay, I'll try to write it. Okay, let's see if I can squeeze it in here. Okay, so if we add all the forces, we get 0 minus 1, 1, 0. Okay, so this equals okay, so sum of the forces, okay, equals 0. That corresponds to these first two rows. Okay, they have to equal the external force in the x direction and the y direction. Okay, now the sum of the moments, okay, because it's a planar, this is a planar problem. The moments are all in the z direction, okay, in the direction perpendicular to the xy plane. Okay, so here's useful thing to remember. Counterclockwise moments are positive. Clockwise moments are negative. Okay, so F1 makes the object rotate clockwise. Okay, so it's going to be a negative moment. And I guess we need to know these dimensions, right? So let's say that this is L1. That is L2. This distance is L3. That distance is L4. Okay, so the first force generates a clockwise moment. So it's going to be a minus L1. Second force F2 generates a counterclockwise rotation, so that's a positive moment. So L2, F3 is L3, F4 is clockwise, so it's a negative moment, minus L4. Okay, and this has to equal the negative of the external moment, and this is in the z direction. Okay. It's getting a little tiresome writing all this, so let me just call it B1, B2, B3. B2, B3. Okay, so there it is. Okay. So here are the equations for static equilibrium. Okay, so now what's the question we ask? We ask the following, right? So this is an equation of the form AX equals B. Okay, so let's call this call this matrix A. Okay, and this vector is x, and here's my B. Okay, so it's equation of the form AX equals B. Okay, so the question now is, does there exist for any arbitrary external force or moment, okay, for any arbitrary B, okay, for any arbitrary B, okay, a solution x, and remember x has to be greater than or equal to 0. Okay, so there it is. Okay, so we reduced it to a question about the existence of a solution to the equation Ax equals B. Okay, so if you think about it, this is, pretty cool, right? That you can reduce this problem to a linear algebra equation of the form Ax equals B. Okay, so how do we answer this question? Okay. So I said, let's think about a simpler version. Okay, so anytime it's hard to grasp something, always think of a simpler version. Reduce the dimension, maybe. That's a good place to start. So we considered, okay, oops, sorry, so it's like that, and then minus 1, 1. Okay, so consider an A of that form. Actually, let's call this AX. So let's put my x here, x1, x2, x3. Okay, equals B1, B2. Okay. All right, so I said let's try to think geometrically. So let's call this column vector A1, call this column vector A2, 2, and this is A3. Okay, so if I draw A1, A2, A3, here's A1, here's A2, here's A3. Okay, so here's A1, A2, A3. Okay, and from this example, okay, I tried to convince you that there's no solution. Okay, for example, if B happened to be in that direction, there's no way that we can come up with a positive linear combination of A1, A2, A3, okay, such that the result is B. Okay, okay, so no solution here. Okay. Okay. Now, if we change A3, okay, to point in the -1 direction, okay, then we have the following picture. A1 points that way, A2 points that way as before. A3 now points that way. A1, A2, A3. Now in this case, a positive linear combination of A1, A2, and A3 can generate any vector in the plane. Okay, so solution X exists, okay, for all B. Okay. All right, so the key thing here is that the directions in which these vectors point, okay, is clearly of essence here. That's what's important. Okay, so the difference here is that if we now connect these three vectors, look at the triangle. Okay, this triangle contains the origin, whereas over here, okay, this triangle does not contain the origin. Okay, so that seems to be the key essential difference. Okay, and this is what makes the solution exist. Okay. All right, so now if we generalize that idea to this problem, okay, now we have four vectors. Four vectors in three-dimensional space. So let's retain this. So let's call this A1, okay, A2, so on, A3 and A4. Okay. Okay, so now let's use that argument again. Oops, let me try to draw it the following way. Okay, so here's my x direction, here's my y direction, here's my z direction. So now if I draw the vector A1, so it's 0, minus 1, minus L1, so maybe it'll be some point like there. Okay, so this will be, say, my A1. Oops. A2 is, oh, sorry, let me try that again. My apologies. So this is my x, this is my y, so minus 1, minus L1. So maybe over here. Okay, so here is A1. A2 is minus 1, positive, so maybe around here. That's my A2. A3 is 0, 1, L3. So 0, 1, L3. So, you know, around there. This is A3. And finally, A4 is 1, 0, minus L4. So it's 1, 0, minus L4. So possibly around here. So there's my A4. Okay. So what we want is that we want A1, A2, A3, and A4 to be pointing in all directions such that if we take their the positive linear combinations, positive linear span, positive span, it covers the entire three-dimensional space. Okay? All right. So another way to characterize that is to look at this. Okay, so we have this. Let me use a different color. Okay, and then we have, I guess, wow, that Okay, so we have this tetrahedron. Okay? And for a solution to exist, what needs to happen? The tetrahedron needs to contain the origin. Okay? So looking at this picture, what do you think? Does it contain the origin? Well, it's hard to say. It's hard to see from the picture. Okay? But if you draw it carefully and you look at it, I think you can convince yourself that yes, the origin does lie inside the tetrahedron. Okay, so let me erase this here. Oops, maybe I shouldn't have done that. Okay. So the tetrahedron should contain origin in its interior, okay, for solution to exist. Solution x, okay, greater than or equal to 0, to exist, okay, for arbitrary b. Okay, and in fact it does. So in fact it does. Okay, so what we can conclude now is that the configuration where the pins are asymmetric is in fact form closure. It can resist any external force or moment. Okay, so if you're going to hang a picture on the wall, that's not a bad way to do it. Okay, of course, the better way is to just drive a nail in the middle. Okay,